Okay, look outside on a clear day, right? The sky is just blue. It's undeniably blue. But then you wait a few hours, sunset comes around, and boom! Suddenly everything's bathed in these incredible reds and oranges. So, why? Why does the universe put on this like amazing dynamic light show? And maybe more fundamentally, why do we even see the world this way? What's actually going on?
It really is one of the most fascinating intersections, isn't it? Physics and
Hmm.
perception just completely intertwined. And today, yeah, we're going deep. We're diving into the fundamental physics, the mechanisms that control everything from, say, the pigment in paint,
Right.
all the way up to why the whole atmosphere looks the way it does.
So our mission for this deep dive is basically to pull together the core physics of light and color and how it interacts with matter. And we should mention our sources, including the really excellent synthesis from Hakiveli Torun, give us a great starting point for tackling this pretty complex stuff.
Absolutely. And to really get color, you kind of have to go back to the beginning, or, well, a beginning. Around 1666, Sir Isaac Newton. He did this experiment. It sounds simple now, but it was genuinely revolutionary. Just a glass prism.
The prism experiment, yeah, classic.
He took ordinary white sunlight, passed it through this prism, and demonstrated that the light split apart into the full rainbow spectrum.
And the big takeaway there, the thing that really flipped everything on its head, was realizing that white light isn't pure. It's not simple.
Exactly.
It's actually made up of, well, all the other colors we see. They're all packed in there together.
Precisely. And that's the core scientific idea. Color isn't some, mystical property floating around. It's directly tied to a physical property of light. It's frequency.
And wavelength, which is related.
In wavelength, yes, they're inversely related. This visible light spectrum we see, it's just this tiny, tiny sliver of the huge electromagnetic spectrum.
Okay, so let's unpack that sliver then. We're talking energy waves, right?
Okay.
From the long, sort of slow, lower frequency waves
Mm.
that we see as red, all the way up the scale to the short, faster, higher frequency waves we perceive as violet.
Correct. Red, orange, yellow, green, blue, indigo, violet. ROYGBV, as many learn it.
Right. And smash them all together, you get white light.
That's the nature of the light itself. But, okay, the next big question becomes, why does matter care? Why does stuff react to light? Why isn't everything just like a shiny white reflection?
Yeah, this is the crucial bit, isn't it? This explains the mechanism, connecting it to the bigger picture.
Yeah.
It's all about the atoms, right? The structure of the material itself.
It comes down to the atomic structure, specifically the electrons. It's all about resonance.
Resonance, okay.
Atoms and molecules, they have these electron configurations that mean they naturally vibrate, but only at very specific frequencies. Think of it like tuning forks.
Okay, so they have their own preferred frequencies.
Exactly. So when light hits the material, the atoms basically absorb the energy from the light waves that match their resonant frequencies.
Ah, so they soak up the frequencies they like.
You can say that.
Yeah.
And the frequencies that don't match, the ones they're not tuned to, those get rejected. They get reflected or sometimes transmitted. And that's the light that reaches our eye. That's the color we see.
So color isn't really in the object itself. It's more like the object's rejection slip for certain light frequencies.
That's a great way to think about it. Yeah. So let's take opaque objects first. How do they get their color through this absorption and reflection process?
Okay.
The principle is, well, beautifully simple when you state it. An object appears, the color of the light frequency it reflects. It absorbs the others.
Right. So the classic example, a red piece of cloth. Why is it red?
That red cloth, its molecules are resonant with frequencies corresponding to, say, green, blue, violet light. So it absorbs those.
It soaks them up.
But it's not resonant with red light's frequency. So
Yeah.
it reflects the red light. That red light bounces off, hits your eye, and your brain says red.
Okay, makes sense. Now the thought experiment you mentioned. What if you take that same red cloth but shine only pure green light on it? No red light at all.
Well, what happens? The cloth is really good at absorbing green light, right? That's
Yeah.
one of its resonant frequencies.
Right.
So it absorbs the green light, but there's no red light hitting it to be reflected.
So, nothing comes back.
Exactly. It reflects basically nothing. So it appears black or, very, very dark. The fabric's redness disappears if you don't give it red light to work with.
Wow, okay. That really drives home the absorption idea. So that's opaque stuff. What about transparent things like, colored glass or plastic film? How does that work?
It's a very similar principle, but instead of reflection, we talk about selective transmission.
Transmission, okay. Going through.
Right. The material still absorbs certain frequency that's resonant with, But the frequencies it doesn't absorb, instead of bouncing back, they pass right through the material.
So red glass.
Red glass appears red because its structure absorbs the higher frequencies, the greens, the blues, the violets, but it lets the lower frequency red light pass straight through to your eye.
Got it. Absorption is still key, but the outcome is transmission, not reflection.
Precisely.
Okay, so now we know how individual objects, opaque or transparent, get their color. But this leads us to the big point of confusion for a lot of people. Mixing colors. Because mixing light is totally different from mixing paint, right?
Oh, completely different. And this distinction is absolutely critical. It really boils down to energy. Are you adding energy together, or are you taking it away?
Adding versus taking away.
Okay, mixing light is additive. You're literally adding different light frequencies, different energy beams together.
Right.
Mixing pigments, like paint or dyes, is subtractive. Pigments work by absorbing light, so when you mix them, you're basically creating something that absorbs more types of light, taking more energy away from what reflects back.
Okay, let's break that down. Additive first, the colors of light.
Right. The primary colors of light are red, green, and blue. RGB. Think about your TV screen, your computer monitor, your phone. They all use RGB.
They're making colors by adding those three together in different amounts.
Exactly. If you shine a red light and a green light on the same spot, what do you see?
Yellow.
Yellow, right? Red plus green light equals yellow light. Red plus blue gives you magenta.
Kind of a purplish pink.
Yeah. And green plus blue gives you cyan, like a turquoise blue-green.
Okay. And the big one, all three together, red plus green plus blue.
You get white light. You've added all the main components of the visible spectrum back together.
So white is the maximum energy state in additive mixing. And you mentioned complementary colors.
Right. Any two colors of light that add together to make white are called complementary. So red and cyan are complementary. Why? Because cyan is already green plus blue.
Ah, so red plus green plus blue.
Yeah.
White. Got it.
Yellow and blue are complementary. Green and magenta are complementary. Same logic.
Okay, that's additive light mixing, RGB. Now, flip it completely, you said, for subtractive colors, pigments.
Exactly. Think paints, inks, dyes. Here the primary colors are cyan, magenta, and yellow, CMY. You often see CMYK in printing. The K stands for key, which is usually black ink, added for depth and practicality.
Right, CMY. So how does this work? It's subtractive.
Right. Remember, pigments absorb light. A yellow pigment looks yellow because it absorbs blue light and reflects red and green, which combine to look yellow. A cyan pigment absorbs red light and reflects blue and green.
Okay. So what happens when you mix, say, yellow paint and cyan paint?
Well, the yellow pigment absorbs the blue light. The cyan pigment absorbs the red light. What's left that both allow to be reflected?
Only the green. Since yellow reflects red and green, and cyan reflects blue and green. Yeah, only green is reflected by both.
Precisely. So yellow paint plus cyan paint gives you green paint. You've subtracted red and blue light for the white light hitting the paint.
Whoa, okay, that's totally counterintuitive compared to light.
Yeah.
So what happens if you mix all three primary pigments? Cyan, magenta, and yellow.
Well, cyan absorbs red, magenta absorbs green, yellow absorbs blue if you mix them all.
They collectively absorb red, green, and blue. Pretty much all the visible light.
Exactly. Since virtually all visible frequencies are being absorbed by the mix, very little light reflects back. The result is black, or something very close to it. It's the minimum energy state.
Black by subtraction, white by addition, completely opposite.
Totally opposite mechanisms.
So my TV screen is using additive RGB light mixing, but the photo I printed out uses subtractive CMY pigment mixing.
Is part of the challenge just our brain constantly merging these two totally different physical processes every day?
That's a fantastic way to put it. And that actually leads us perfectly out of the sort of controlled lab examples and into the real world. Because this raises the big questions we started with. Okay, we understand objects now, but why is the sky blue? Why are sunsets red?
Right, it's not paint, it's not glass.
It's the atmosphere itself. And the key phenomenon here is scattering.
Scattering, like light waves bumping into stuff in the air.
Pretty much. Sunlight comes into the atmosphere and it collides with the tiny gas molecules, nitrogen, oxygen, all that stuff. These collisions cause the light waves to deflect, to scatter off in different directions. Okay, but why does that make the sky blue?
Because the scattering isn't equal for all colors. It's highly dependent on the wavelength of light compared to the size of the particle doing the scattering. For tiny air molecules, they are much more effective at scattering short wavelength light.
Short wavelengths. Like blue and violet.
Exactly. Blue and violet light get scattered far more strongly, something like 10 times more effectively than longer wavelength red light.
Wow.
10 times.
So when you look up at the sky, away from the direct path of the sun, the light you're seeing is light that has been scattered by the air molecules.
Oh.
And since blue light is scattered so much more intensely,
That scattered blue light dominates what you see coming from all directions, making the sky look blue.
that's the essence of it. Our eyes are also slightly more sensitive to blue than violet, and the sun emits a bit less violet, so blue wins out overall for our perception.
Okay, that explains the blue sky. But then what about dawn and dusk? The whole dynamic flips. Why the intense reds and oranges?
It's the same principle scattering, but applied to a different situation. Think about the path the sunlight has to take to reach you when the sun is low on the horizon.
It's going through way more air, right? A much thicker slice of the atmosphere.
Exactly, an exceptionally long path. And over that long journey through dense air, what happens to the short wavelength light?
The blue and the violet. They get scattered away even more.
They get scattered away laterally, out of the direct path from the sun to your eye. Almost all of the blue, the violet, even a lot of the green gets removed from that direct beam by scattering.
So what's left? What makes it through that long haul?
Only the longer wavelengths, the ones that don't scatter as easily, the reds and the oranges, they power through that thick atmosphere more or less directly to you.
So the light that survives the trip is reddish, making the sun itself and the clouds around it look red or orange. It's like atmospheric filtering.
Selective removal by scattering over a long distance. That's it.
Amazing. Okay, while we're in the atmosphere, clouds. Why are they usually white if the sky is blue?
Ah, good question. This comes down to the size of the scattering particles. Air molecules are tiny, much smaller than the wavelength of light. Cloud particles, water droplets, or little ice crystals are much larger.
Okay, bigger particles. How does that change scattering?
When the scattering particles are large compared to the wavelength of light, they scatter all wavelengths, all colors, much more equally. It's called scattering, as opposed to the Rayleigh scattering that makes the sky blue.
So they're non-selective scatterers. They just bounce all the colors around equally.
Right. Since they scatter red, green, blue, all the colors pretty much the same amount, the light coming off the cloud is essentially white light, the same mix that came from the sun.
Unless they're really thick storm clouds, then they look gray.
Well, yeah. If they get thick enough, less light makes it through them. Some light gets absorbed within the cloud, so they look darker, grayer. But the scattering itself is still mostly non-selective by color.
Okay. And one last natural phenomenon the sources mentioned, deep water. Why does deep water often look kind of bluish-green or turquoise?
That's actually about absorption again, but by the water molecules themselves. Water happens to be naturally quite good at absorbing longer wavelength light.
Longer wavelengths, like red.
Specifically red light, yes.
Yeah.
Water absorbs red light more readily than it absorbs blue or green light.
So in shallow water, it doesn't matter much.
Not much, no. But in really deep water, sunlight penetrates down, reflects off maybe the bottom or particles in the water, and has to travel back up again. That's a long path through water.
And over that long path.
Over that long path, a significant amount of the red light gets absorbed by the water molecules. So the light that eventually makes it back out to the surface and reaches your eye is noticeably depleted in red.
Leaving mostly the blues and greens, which mix to look turquoise or bluish-green.
Exactly. It's the selective absorption of red by the water itself.
Wow. Okay. So we started with Newton and a prism, and we've ended up explaining turquoise oceans. That's quite a journey. We've basically covered the three big ideas, right? First, color is fundamentally about the frequency of light.
Yep, physical property.
Second, objects get their color mostly by selectively absorbing some frequencies and reflecting or transmitting others. Resonance is key.
Absorption and reflection, or transmission.
Mm-hmm.
And third, these big, beautiful natural colors like blue skies and red sunsets are governed by how light scatters off particles, and that scattering depends heavily on frequency.
Frequency-dependent scattering. Yeah, those are the core principles.
So, pulling it all together,
Yeah.
what's the final takeaway here?
Well, one interesting point from the sources is about the sun itself. If you look purely at the physics, the sun's peak light emission, its brightest output, is actually right in the middle of the spectrum, in the yellow-green frequencies.
Really? Not white, yellow-green.
In terms of raw energy output, yeah.
Yeah.
But by the time that light gets filtered by our atmosphere and then processed by our eyes and our brain's interpretation, we perceive it differently. We don't usually look up and think, oh, the sun's yellow-green today.
Right. Our whole system, atmosphere, eyes, brain, modifies that initial physical reality. It absolutely does. Which leads to maybe a provocative thought to leave folks with.
Okay.
We've talked about how your TV or computer screen uses additive RGB light mixing, and how a printer uses subtractive CMY pigment mixing. Two totally different physical processes working on opposite principles.
Right. Additive versus subtractive.
So think about this.
Mhm.
Every single time you look at a photograph printed on paper, and then maybe you look at the exact same image displayed on your phone screen,
Hmm.
or you just look out the window at the actual horizon.
Yeah.
Your brain is taking these fundamentally different physical ways of creating color, adding light energy, subtracting light energy via absorption, scattering by the atmosphere, and it's instantly, effortlessly synthesizing them all into one single coherent visual experience of the world.
Whoa, it just merges these opposite realities without us even noticing.
Exactly. The reality of color isn't just the physics. It's always this constant, incredible conversation happening between the physics of light and matter and the biology and psychology of our perception.